Hey everyone, Dr. D here, and in this video we are going to be covering Chapter 8 from our Campbell's Biology 12th edition, so let's go ahead and get started.
Dr. D, Dr. D, Dr. D. Dr. D, Dr. D, Dr. D. Dr. D, Dr. D, Dr. D. Explain stuff.
Alright, let's go ahead and get started. This is actually my first video on my new computer rig that I put together yesterday, so I hope it brings you some better video quality. I'm going to be trying to up the quality, maybe not in this video, but in the subsequent videos, try to get more resolution in the videos and work on my editing with a stronger computer. So I'm excited about that. So let's see how that goes. I'm excited. This is my first video on this new computer. I hope everything works out. So let's go ahead with Chapter 8. Chapter 8 deals with metabolism. Now, when we're dealing with metabolism, you should know that metabolism refers to the totality, that means all, of an organism's chemical reactions. So every chemical reaction occurring in your body right now constitutes your metabolism. And a metabolic pathway is a specific molecule altered in a series of steps to produce a final product. Each step is catalyzed by a specific enzyme. So when we're talking about a metabolic pathway, you can think of it like this. You take some starting molecule, like molecule A. Enzyme 1 will change molecule A to molecule B. Enzyme 2 will come along and change molecule B to molecule C, and then enzyme 3 comes along and changes molecule C to molecule D. This is what they mean by a metabolic pathway. You start with some substrate A, and you want to produce a product D, but there are intermediate steps along the way. This is known as a metabolic pathway. Normally, metabolic pathways require these intermediate steps, as well as multiple enzymes along the way. Now, metabolism includes two major branches: catabolic metabolism and anabolic metabolism. Those are the two major branches. Let's talk about the first one, catabolic metabolism, also known as catabolic pathways. These catabolic pathways release energy by breaking down complex molecules into simpler compounds. So when you think of breaking down macromolecules into monomers, that's what we're talking about. When you're breaking down more complex structures, usually with enzymes, and you're breaking them down into smaller, more numerous substances, this is known as catabolic metabolism. So for example, we're going to learn about cellular respiration, the process by which your mitochondria break down glucose to produce ATP. Remember that? That's an example of catabolic metabolism. And usually, catabolic metabolism results in release of energy. Okay, think about that. You're breaking things down and releasing energy. Usually you release energy. In anabolic pathways, on the other hand, anabolic pathways, these are the other major branch of metabolism. Here, you're trying to build more complex molecules. So for example, when you link two monosaccharides together to make a disaccharide, or when you put amino acids together to build a protein, this is called anabolic metabolism or anabolic pathways. These consume energy, so they require energy to build complex molecules. So for example, like I said, when you build a protein from amino acids, again, two major branches of metabolism: catabolic, where macromolecules are broken down, complex molecules are broken down, and anabolic, where they are built. Catabolic pathways release energy, they provide energy. Anabolic pathways consume energy, they require energy. So I've said energy a few times now, but what does energy mean? How do you define energy? Energy is the capacity to cause change. Energy can be used to do work. energy exists in various forms. There are many different forms of energy, and that's kind of why energy has such a vague definition. You see how energy is defined as the capacity to cause change? That's a pretty vague definition, right? It's not a very concrete definition, and that's because energy can exist in so many different forms. The only thing those forms have in common is that they have the capacity to cause change. And living cells, like the cells in your body, they are constantly transforming energy from one form to another all the time in order to allow life to occur. So let's explore some of the various forms of energy, starting with kinetic energy. Kinetic energy is the energy associated with motion. Anytime something is moving, it possesses kinetic energy. Even if molecules are moving, that is said to be kinetic energy. And you can use moving objects to perform work by imparting motion to another object or other matter. So for example, water gushing through a dam can turn turbines. You see, so that's the kinetic motion of water turning turbines, which can be used to produce, let's say, electricity. Isn't that interesting? So kinetic energy is the energy associated with motion. Next, thermal energy. Thermal energy is actually, in a weird way, a type of kinetic energy. But it's kinetic energy associated with random movement of atoms or molecules. So this is at the atomic scale. If individual molecules are moving quickly, that means that they possess thermal energy. So for example, I'll give you an example. Here's my awesome Dr. D thermos from a student of mine who actually created this for me, and on the back there's the whole photosynthesis, the process of photosynthesis, an amazing art project. But let's pretend I have coffee. I have coffee in my thermos here. If my coffee is hot, if it has thermal energy, that means that my coffee, the water molecules in my coffee are actually vibrating quite quickly. They're moving quite quickly. And that water's moving fast. And that's what hot coffee is. Now, if I left this mug or this thermos out for a while and my coffee became cold, the only difference is it's still coffee in there, but those coffee, that water is moving much slower. Those molecules are vibrating much slower than they did before, so they possess less thermal energy. So think about that. Thermal energy is a type of kinetic energy, isn't it? Because kinetic energy means motion energy, and the difference between a hot coffee and a cold coffee is simply how fast its molecules are moving, right? So when I say thermal energy is simply kinetic energy at the molecule scale. Hi, Wicket. Hi. Wicket's come to say hi, you guys. Did you hear him meow? Hi, Wicket. Come say hi. Awesome. I always enjoy when Wicket comes to say hi. All right, you guys are getting a glimpse at his tail. So again, thermal energy is a type of kinetic energy associated with the molecules themselves. And thermal energy in transfer from one object to another is known as heat. This is called heat. Hi, little guy. Hi, Wicket. Wicket is here to say hello to everybody. Hi, Wicket. Wicket is pawing at the screen. I'm sorry, you guys. So again, when thermal energy is transferred from one object to another, this is known as heat by Wicket. Light is another type of energy that can be harnessed to do work, such as photosynthesis, right? So light is another type of energy, but this is photo energy or sunlight energy. Next, potential energy. This one's probably the most difficult one to wrap your brain around. So potential energy is energy that matter possesses because of either its location or its structure. Here's an example from your book. Water behind a dam possesses energy because of its altitude above sea level. That's an example of potential energy due to its location. So for example, if I hold something up above my head, it's said to have high potential energy. But if I place that same object on the table, it has less potential energy. Because think about it, if I hold something way up here, it has high potential energy because if I were to let go, you see, it would convert that potential energy to kinetic energy as the object falls. You see how holding something up high increases its potential energy because that potential could be converted to kinetic, right? However, if I placed this same object on the table or on the floor, it would be said to have less potential energy because it lacks that potential to convert its energy to another type, right? Now, that is an example of potential energy based on location. But what about structure? Okay, let me explain structure. How does potential energy play a role in structure? So for example, let me give you a bow and arrow example. If you have a bow and arrow, right? And if you pull the bow all the way back and you've got strain and stress on that bow, at that point, even though you're not technically doing anything, that bow, which is pulled back, is said to have high potential energy, but not because of its location. It's not because I'm holding the bow above my head or placing it on the ground. It's because it's strained like this. Because if I were to let go of that bow, then the arrow would go flying, right? It would convert that structural energy, that potential energy in the form of that structure of me pulling back on the bow with the arrow, to kinetic energy. When I let go of the bow, the arrow would go flying. So I had converted the potential energy of the bow to kinetic energy of the arrow flying across to the target, right? So when you hear about potential energy, just remember that potential energy can exist in location, so up high, or structure, like a bow and arrow. Think about it that way. What about chemical energy? Did you know that chemical energy is actually a type of potential energy? Just like thermal energy. Do you remember thermal energy was a type of kinetic energy? Just like that, chemical energy is a type of potential energy. But let me ask you this. Let's get you to think a little bit. Let me ask you this. Let's see if you can beat Wicket to the answer. Do you think chemical energy, so for example, a chemical with high energy, like sugar, right? Sugar has a lot of energy. Sugar has high chemical energy. Do you think sugar has high chemical energy because of its potential energy in the form of its structure, or is it because of its location? That's right, Wicket. The location of the sugar doesn't matter. It's the structure of the sugar molecules, right? So glucose has high chemical energy, and that's because of its chemical structure, right? The structure of that sugar molecule is what makes it a high chemical energy molecule. Isn't that interesting? So chemicals, high energy chemicals like glucose are high in chemical energy because the energy is released as they are broken down into simpler products, and that was because of their bonds. It was because of their structure. And as I've been mentioning all along, you can convert one form of energy to another. For example, chemical energy from food, when you eat sugars and fats, is used to perform the work of climbing up to a diving platform. The kinetic energy of muscle movement is transformed into potential energy as the diver climbs higher above the water. The potential energy is then transformed to kinetic energy as the diver falls back down to the water. You can transform and you can convert one form of energy to another. Remember I said when I held the pen above my head, it had high potential energy, but when I let go, I converted that to kinetic energy. So you can convert one form of energy to another, transform one form of energy to another, and that's a property of energy. So again, here's that example. The diver climbing up the ladder using kinetic energy to climb up the ladder converts that kinetic energy into potential energy. The diver has more potential energy on the platform than in the water. And then that diver can convert that potential energy to kinetic energy, falling back into water. And the diver has less potential energy in the water. And the diver has to put in its own kinetic energy to get back up onto the platform. Does that make sense? So you can see here how energy can be transformed from one form to another. For example, from kinetic energy and from kinetic energy to potential energy and back again. Now, we've talked a little bit about energy transformation from kinetic to potential, for instance. But there's a whole field of study that focuses on energy transformation. And this field of science is known as thermodynamics, the study of thermodynamics. Thermo meaning heat and dynamics meaning movement. So thermodynamics is the study of energy transformations in a collection of matter. And people who study thermodynamics, they are trying to understand how energy works and how energy is transformed. But first, they have to define their system. So, for example, we're not going to go into too much thermodynamics, but you should know that in an isolated or closed system, the thermodynamics work a lot more in a different way than in an open system. Do you remember my thermos example back there? You see that thermos over there? That would be an example of an isolated thermodynamic system where whatever is happening in that thermos is unable to exchange energy or matter with its surroundings, right? So if you're studying thermodynamics, the study of energy transformations, and you're studying what's happening in a perfect thermos, then whatever's happening is just happening in that thermos, and the surrounding environment has no effect on that, okay? But do you think that you and I and other animals and living life forms are isolated systems? Like, is our body an isolated system that has nothing to do with the environment and does not exchange matter or energy with the environment? That's right, Wicket. No way. We are open systems. So in an open thermodynamic system, energy and matter can be transferred between the system and its surroundings. Organisms are open systems. They absorb energy from light or food. They can release heat and metabolic wastes, such as CO2, to the surroundings. So the universe and the environment can affect us. We can affect the environment. We are an example of an open thermodynamic system. And so that's what I need you to remember, is that when scientists study life and biology and they want to know how energy works in a biological system, you need to keep in mind that biological organisms are open thermodynamic systems, not closed or isolated ones like a thermos. Now, when discussing thermodynamics, there are various laws of thermodynamics to understand. Two of them we're going to cover now because they directly play a role in understanding how a cell functions. So let's talk about the first and second laws of thermodynamics. The first law of thermodynamics is also known as the principle of conservation of energy, and it states that the energy of the universe is constant. This means that energy cannot be created nor destroyed. The same amount of energy is available to the universe today as it will be tomorrow, as it will be a billion years from now, or a billion years ago. The energy can only be transferred or transformed. You can transfer or transform energy all day long, right? From potential to kinetic to electrical. But what you can't do is create energy nor destroy it. And this leads us to the second law of thermodynamics. According to the second law of thermodynamics, every energy transfer or transformation increases the entropy of the universe. The term entropy is a term that refers to a measure of molecular disorder or randomness. So entropy, also depicted as units of capital S, is a measure of disorder. So the more disorder exists, the more entropy there is. Now, students ask me all the time, Dr. D, what do you mean by disorder? What is entropy? Well, just like there are different forms of energy, there are different forms of entropy. So entropy exists in many different ways. One example is anytime something breaks apart. Like if I have this marker here, you see, or this highlighter, you see how this highlighter is one piece? What if I were to break this highlighter in parts, right? So if I were to remove the cap, now I have two parts, you see? That is more disordered than having one part, okay? So anytime something breaks down, a molecule breaks down into 2 or 4 or 10, if something breaks down, you have increased entropy. You have increased disorder. So one form of disorder or entropy is things breaking down. Another form of disorder occurs when molecules drift apart or move apart. If I were to say release a gas and those molecules are all close to one another, that's said to have more order than if those molecules all drift apart. You see, so if those molecules are drifting apart, that is an increase in disorder. So anytime diffusion occurs, molecules move apart, that is more disorder. Here's another example of more disorder. Heat. Heat is always an example of disorder. Heat is disorder. Heat is the random movement of molecules transferring from one body of matter to another. Heat is an example of disorder. Here is another example of disorder. When matter moves from solid state to liquid state, that is more disorder. So liquids are more disordered than solids. Why? Because think about it. Do you remember what I said ice is? Remember ice? We talked about ice. Ice was when all these water molecules formed this perfect crystal lattice with one another, forming hydrogen bonds with one another. And that was a beautiful crystal that formed, that ice crystal. Those molecules are all arranged nicely and organized. So that's not very chaotic, is it? That's not very disordered. However, if you warm up that ice and it becomes liquid, you break those hydrogen bonds and those water molecules are moving all about, right? And that is more disordered than the solid state. Now, what if I were to heat the water more and more and more, and then the water became vaporized, right, into gas, right, water vapor? That's even more disorder. So gases have the most disorder, liquids have less disorder, and solids have the least disorder. So that's another example of disorder. So I hope I gave you some examples of disorder. Just like energy has different forms of energy, disorder has different forms as well. So now that you understand some examples of entropy or disorder, and you understand that according to the second law of thermodynamics, the entropy of the universe should be increasing more and more, it might be perplexing to recall that life itself is order, right? Remember, one of the characteristics of life is order. So people were wondering why life came to be. How did living organisms come to be if one of the characteristics is order? But if the universe is heading towards more disorder, as the second law of thermodynamics states, isn't that a paradox? You know what a paradox is? Where it seems like opposing things are true. You know, how can two opposing things be true? How can the universe be headed towards more disorder, but life, which is an example of order, come to fruition, come to be? So this was an interesting paradox, which is exemplified here by the bear. Here you have the brown bear, and he's hunting. And he's hunting for food in the form of fish, chemical energy. The bear feeds on the chemical energy and then runs about and does its thing. Now, the bear, even though it looks like he's just fishing and having a good time here, he really does exemplify life and explain in his own way how the paradox of the second law of thermodynamics can be explained. So let me explain. What is the bear doing? The bear has to seek out nutrition, right? The bear has to seek out chemical energy in the form of food, right? To eat fish, to obtain sugars and fats, chemical energy. And the bear will then use that chemical energy, remember, which is in the form of sugar and fat. And the bear's body will change that sugar and fat into ATP energy. It will transform the energy from sugars and fats into ATP in order to run about and, hunt some more and to live. In the process, the bear breaks down those big sugar molecules, those big glycogen molecules. It breaks down those big fat molecules. And it breaks those down into numerous CO2 and H2O. So let me ask you this. If the bear is breaking down large macromolecules like glycogen, right, as well as large fats, which, remember, have a glycerol head and 3 fatty acid tails, and you're breaking down these large complex molecules into numerous CO2 and H2O, and that's what's left of your sugars and your fats, and that's what the bear's breathing out. Is the bear producing disorder? Yes, the bear is producing disorder. The bear is breaking down complex molecules into CO2 and water. And also the bear is also moving about, releasing heat. And remember, heat is also an example of disorder. So the bear is like a disorder machine, is it not? The bear is moving about. It's breaking down complex molecules. Remember I told you, like the pen, when you break the pen down into two, that's more disorder, isn't it? So when you break sugars down into CO2 and water, or when you break fats down into CO2 and water, you are increasing disorder. And when you're releasing all that heat in the process, you are releasing disorder. So the bear, you can think of the bear, and the bear is a stand-in for life, living organisms. The bear is a disorder machine. The bear creates tons and tons and tons of disorder. And in a weird way, that pays what's called an entropic penalty to the universe. So the bear is creating enough chaos, enough randomness, enough disorder and entropy to pay for its own order, right? It's like it's paying its taxes to the universe. It's creating so much disorder that its own cells and its own tissues, its own organs can be ordered themselves, and thus not imposing on the second law of thermodynamics. It does not negate the second law of thermodynamics, that living things are ordered. That's because each living thing is a disorder machine that creates more than enough disorder to pay for the order. I hope that made sense, but this shows that the second law of thermodynamics does not contradict life. Now, processes that increase the entropy of the universe can occur spontaneously. What's spontaneous mean? A spontaneous process occurs without energy input. It can happen quickly or slowly as long as it does not require energy input. In fact, spontaneous processes, not only do they not require energy input, they release energy. Processes that decrease entropy are not spontaneous or non-spontaneous. They require an input of energy. So if overall a process, let's say a chemical reaction, increases entropy, then it's spontaneous. But if overall that chemical process does not increase entropy, then it would be non-spontaneous. Now, biologists follow the energy and entropy changes during chemical reactions inside of the cell to determine whether they require an input of energy or whether they occur spontaneously. Remember, spontaneous process, these ones occur without any energy input. In fact, they can release their own energy, while non-spontaneous processes require energy input in order to proceed. Now, in order to understand how energy works, a gentleman by the name of Gibbs coined free energy. And now the capital letter G, after his own last name, is the unit for free energy. Free energy is the portion of a system's energy that can do work when temperature and pressure are uniform throughout the system, as in a living cell. Now, I'm going to give you some examples of free energy, but for now, just keep in mind that free energy is a system's energy that can do work. Okay? Now, let me give you some examples to help solidify this concept. So think of free energy as the total available energy to do work, right? A system's free energy to do work. So this gentleman on the platform, would the gentleman on the platform have higher free energy, so higher ability to do work, or the person when he's in the water? Which one do you think has higher free energy, more ability to do work? That's right, Wicket. The gentleman on the platform, because he has high potential energy, because of his location, he has a higher free energy. So this would be a high free energy state. And in the water, you would have a low free energy state. Okay, here's another example of high free energy. When these molecules of dye are all close together like this, like let's say I put a drop of dye into a beaker of water. At first, that drop is highly ordered, and that is a high free energy state. There's more free energy. Then, after those drops of dye diffuse across the beaker, they form a low free energy state. Okay, that's another example of high free energy to low free energy. Here's one last example for you of a high free energy state. This is sugar, so glucose. So glucose is a molecule with high chemical energy, so this is a high free energy state. After this sugar molecule is broken down into CO2 and water molecules, this is a lower free energy state. Okay, so all of these examples on the top row of this diagram, all of these examples are high free energy states, so they would be high G values, and all of these across the bottom are low free energy states. They would have a lower G value. The high free energy states are less stable with greater work capacity, while the lower free energy states down here are more stable with less work capacity. Now again, just to review, these are all high, I put an arrow upwards, high G value states. High G, this is a high G value, and this here is a high G value, a high free energy, right? The sugar molecule has high free energy. And across the bottom, remember, this is low G value. It's a down arrow, low G value. And here you have a low G value. G value is low. And again, you have a low G value. Up here, you have high free energy. Down here, you have low free energy. Now, I want you to look at this. When the diver goes from a high G value position to a low G value position, what we say is that the change, and you guys know from math, change is denoted as a triangle, which is known as delta, the Greek letter D, delta. The change in G is what? Let me ask you this. When you go from a high free energy state, like the man on the platform, to a low free energy state, like the man in the water, how does that affect your change in G? Well, you went from a high G to a low G. Does that make sense? So your change in G was a negative change in G. Same thing when you went from a high G value to a low G value with the ink droplets, the ink molecules spreading apart. That's a negative change in G. And lastly, that's also the same story when we go from a high G value to a low G value, going from a sugar molecule to CO2 and water. This is a negative change in G again. These are all negative delta Gs, negative change in Gs. So what that tells you is that when you go from a high G value to a low G value, this is going to result in a negative delta G. And by the way, these are all known as spontaneous reactions. When a reaction has a negative change in G, this is known as a spontaneous reaction. And conversely, when the diver goes from the water back up to the platform, what is the change in G then? It's a positive delta G. What about trying to get your ink droplets back, right? If you tried to get your ink droplets back together into one drop of ink, that would be a positive delta G, right? Trying to get the energy, get the ink molecules out. And what if you made a sugar molecule from CO2 and water? That would also be going back up, right? So that would be a positive change in G. Did you see that? I'm sorry, I don't know why this thing doesn't draw well on PowerPoint. So again, when you go from a high G value to a low G value, this is known as a negative delta G, and that's a spontaneous process. When you go from a low G value back to a high G value, this is known as a non-spontaneous process. This has a positive delta G. And so what I want you to remember is that any process with a negative change in G, a negative delta G, is a spontaneous reaction, while any process with a positive delta G is a non-spontaneous reaction. Spontaneous reactions occur without input of energy. Non-spontaneous reactions require energy to happen. And that makes sense, right? That makes sense. Let me clear this. Okay. That makes sense, right? For this diver to go back up onto the platform, the diver would have to put in energy to do it. If you wanted these ink molecules back, you would have to put in energy to get these back as a drop of ink. If you wanted to make a sugar molecule from CO2 and water, that would require you to put energy in. Do you see how all of these across the bottom would require energy to achieve the top row status again? Okay, so that's what we mean by spontaneous and non-spontaneous. So again, with free energy, you can think of it as a measure of a system's stability. Unstable systems have a higher G. They then tend to become more stable with a lower G. Remember, and this is a negative change in G. This is a negative delta G. That's a spontaneous reaction. For example, remember, the diver on the platform is less stable than when floating in the water. The drop of concentrated dye is less stable than when it is dispersed randomly throughout a liquid. The glucose molecule was less stable than the simpler molecules like CO2 and water in which it can be split. So you can think of these as not just high free energy or high G value states, but less stable states as well. And what is equilibrium? I told you what a positive G value and a negative G value mean, right? So when a process has a negative delta G, a negative delta G means spontaneous reaction. A positive delta G is a non-spontaneous reaction. But what happens at equilibrium? Delta G equals 0. So equilibrium is the point at which the forward and reverse reactions occur at the same rate. Describes a state of maximum stability. So now we know what delta G means, right? Change in free energy. But what does delta G depend on? What other variables can change this value? The change in free energy during a reaction is related to temperature in Kelvin, T is temperature in Kelvin of the system, as well as changes in enthalpy is H, and entropy, as you know, which is S. So this is known as the Gibbs equation, where if you want to understand change in free energy during a reaction, you have to understand what's happening with enthalpy, which is the change in enthalpy or total energy, and delta S, which is change in entropy. As you know, that's disorder. Now, to explain how this equation works, the Gibbs equation in detail, let's head over to the whiteboard, where I will break down this equation and break it down in a way that hopefully makes sense, and shed some light onto Gibbs's findings and some of these principles of thermodynamics. All right, let me explain Gibbs equation. This equation allows researchers to understand whether a reaction is going to be spontaneous or not spontaneous. And remember, that has to do with delta G. Remember, a negative delta G, I'm going to write this out. A negative delta G would mean that the reaction is spontaneous. Whereas remember, a positive delta G would suggest that the reaction is non-spontaneous. Okay? We know that part already, but what does delta G depend on? What other variables can affect our delta G value? Well, this is it. We have these values H for enthalpy, T for temperature, and S, as you already know S, right? What did S stand for? That's right, Wicket. Entropy, disorder. We know disorder, S, okay? So it turns out that H, T, and S play a role in our, free energy change, okay? Now let's break this down some more. Let's break it down a little more, okay? Let's just define our values. So delta H, okay, again, I said H is for enthalpy, enthalpy. Enthalpy. All right. And enthalpy refers to total energy. But the way I like to think about it is heat. Okay, think of it as heat. Now, bear with me on this. If there's a negative change in enthalpy, a negative delta H, okay? If there's a negative delta H, a negative change in enthalpy, this means that the system has lost total energy, which means it's lost heat, okay? This means that heat has been released. So, for example, if I mix test tube A and test tube B, and then I feel the test tube, oh, and it's getting hot. It's getting hot. That's because it's releasing heat. It has a negative delta H. That would be an example of a negative delta H reaction. So what's the opposite of that? A positive delta H reaction, which would mean what? It would mean heat is absorbed. I know that's weird wording, isn't it? This would mean that if I mix those chemicals, and if this was a positive delta H reaction, heat is being absorbed. It has a positive change in enthalpy. That means if I were to touch the test tube, it would be cold, right? Why would it feel cold? Well, because it's absorbing heat. Real quick, just a sideline for you. Do you know why I said this is not releasing cold, it's absorbing heat? That's right, Wicket. Heat moves. Cold is simply the lack of heat. Does that make sense? Cold isn't a real entity. Cold doesn't move anywhere. Cold's not even a real thing. Cold is simply the absence of heat. So when something feels hot, it's because it's releasing heat into your hand, and your brain interprets that as hot, okay? But if something feels cold, it's not that it's transferring cold to your hand, it's actually sucking the heat out of your hand because it's absorbing all the heat. Does that make sense? So your brain interprets things that are cold as things that suck heat out of your hand. Isn't that interesting? So if a reaction feels cold after you've mixed the two chemicals together, that's because it has a positive delta H. Heat has been absorbed. And yes, the other terminology for it is if it's releasing heat, this is an exothermic reaction. And if it's absorbing heat, this is an endothermic reaction, okay? So hopefully that makes sense. We're just breaking down the different variables here, okay? We're breaking them down so we understand the full equation before we delve into what does this equation mean. And on that note, remember, negative delta G means spontaneous. Another term for a negative delta G or spontaneous reaction is known as an exergonic reaction. So when I say an exergonic reaction or an exergonic process, I'm talking about a spontaneous process. I'm talking about a process with a negative delta G, okay? Conversely, a non-spontaneous process or a positive delta G reaction is actually known as an endergonic. Endergonic reaction, okay? So don't mix up these terms. Exergonic means negative delta G. Exothermic means negative delta H. Endergonic means positive delta G. Endothermic means positive delta S. Don't get these terms confused. I know it's confusing because they look very similar. Don't get confused. All right, let's move to delta S. Let's talk about S. We already know what S is, don't we? We discussed the second law of thermodynamics, you know, that entropy is increasing every time there's energy conversion or transformation. All right, we know that. So S is the unit for entropy, disorder, right? Disorder. So let me write that down. S is for disorder. And here we have delta S, which means change in S. Well, if we have a negative delta S, if we have a negative change in S, this actually means we have less disorder. Less disorder. You could think of it as more order if you want, but it's less disorder. So for example, I'll give you an example. If I mix chemical A with chemical B, right, and they're two liquids, I mix two liquids together, and suddenly those two liquids form a solid, right? Do you remember what I said earlier? That solids have less disorder than liquids, right? So if I were to mix two liquids together and they were to solidify, that would be a drop in disorder, isn't it? That's going from a liquid to a solid. Solids are inherently less disorderly than liquids, so that would be an example. I'm just giving you an example of a reaction that has a negative delta S, less disorder. Now, conversely, what if I added tube A and tube B? What if I added two chemicals together and it started bubbling up and turning into a gas? You know, when it bubbles, that means it's converting to gas, right? That's what bubbles mean. It's bubbling, and then it just explodes into gas and into a bunch of particles everywhere. That would be a positive delta S reaction, right? So more disorder. Positive delta S means more disorder, right? So again, anytime a solid goes to a liquid goes to a gas, anytime some large thing breaks down into smaller pieces, we got more disorder, right? When things come together or solidify, when things come together, we have less disorder. When things break apart, we have more disorder. Does that make sense? All right, so we've got one more value here to understand, and that's T. All right, the last variable here, T, we're talking about T is for temperature. The temperature in Kelvin. Okay, so T stands for our temperature in Kelvin. Now you might be confused. Let me address your confusion. You might be confused. You might be thinking, but Dr. D, I thought you said, if the reaction's releasing heat, it's got a negative delta H. If it's absorbing heat, it has a positive delta H. What is this? This is temperature. We already talked about temperature. There's a difference, right? This temperature refers to the temperature at which you did the experiment, at which where the reaction occurred. So, for example, if I mix two chemicals at room temperature, this Kelvin would reflect temperature in Kelvin, right? The temperature of the room in Kelvin. Okay. Regardless of if the reaction gets hot, well, that would be a negative delta H, or cold, that would be a positive delta H. That's not the point. The point is, at what ambient temperature did that reaction occur? Does that make sense? That's what we're talking about with Kelvin. All right. Now, one thing I need you to know about Kelvin is that unlike degrees Fahrenheit or degrees Celsius, you cannot reach 0 Kelvin, practically. you can't reach 0 Kelvin, and you can't go negative. It's impossible to have a negative Kelvin. Does that make sense? So what I want you to know about Kelvin is very straightforward. This isn't a physics class or an advanced chemistry class, so we're not going to go into like every parameter of this equation, but I want you to do this favor for me, okay? In order to facilitate your understanding of this equation, because I want you to understand this equation, okay? The way I'm going to do it is by simplifying something. Bear with me, okay? What I want you to know is that I want to ignore T, right? I want to ignore temperature. How can I just ignore temperature for the purpose of understanding this equation? Well, all I know is that T stands for Kelvin, and I know Kelvin can't be 0. Does that make sense? Kelvin cannot be 0, and Kelvin cannot be negative, right? So doesn't that mean that Kelvin must be a positive number, right? Are you following me so far? Kelvin is a positive number, is that right? So what I like to do when I'm instructing students, when I'm teaching this concept, is just pretend our temperature is 1. Okay, I just pretend our temperature is Kelvin of 1. Not because the temperature really is 1 Kelvin, because that would be super cold, okay? But because if I put a 1 here, doesn't that really simplify this equation? Think about it. Is 1 a positive number? Yes. If I put a 1 there, does it simplify this already simple equation even more? Yes, because I could just ignore it, right? If it's 1, it can kind of disappear, and we could just focus on this part of the equation. Does that make sense? You guys follow me? So that's why I like to set Kelvin to 1, because then we can ignore it, because 1 times anything is that thing, right? So it's 1 times delta S. So I just kind of ignore it, okay? And now we can talk about this part of the equation. Now we can really get in there and talk about what the rest of the equation means, okay? And that's what we're going to do next. I want you to really understand what Gibbs brought to light. All right, let's break this thing down. We're ignoring T because we set it to 1 to forget it for now. Not that it's not important, but because we don't need it right now for our understanding. We just have a very simple math problem, don't we? Delta G equals delta H minus delta S, right? So it's just this minus this equals that. It's, grade school math, okay? What does it mean to have a negative delta G? If delta G is negative, okay, let me ask you this. If delta G is negative, what does that mean? That means it's a spontaneous process, right? So when the value of delta H and delta S give you a negative delta G outcome, then that's going to be a spontaneous process, right? So I'll give you an example. Ready? Okay, I want you to work on this as I say it. Try to beat Wicket. If I mix 2 chemicals and it starts bubbling and getting hot, let's say getting hot. Oh gosh, it's getting hot to the touch. What's my delta H? Is it a positive delta H or a negative delta H? That's right, Wicket. It's a negative delta H. So let's say, again, I'm doing this experiment where I have a negative delta H, and that's because I mixed 2 chemicals and it got really hot, okay? And what did I say it was doing? I said it was bubbling over, right? Does that make sense? It was bubbling over. That means conversion to gas. That means more disorder, right? So what would my delta S be? Would my delta S be positive or negative? Right, again, Wicket, it's a positive delta S, right? So if I were to plug in, I would have a negative delta H minus a positive delta S, which anytime you minus a positive, you can just ignore that positive, right? So in this case, we just figured it out. I mixed chemicals A and B. It felt hot, so I have a negative delta H and it bubbled over. So I have a positive delta S. But the equation tells me to subtract that positive number. Okay, you following me? Now, riddle me this. What is my delta G? If I take a negative number, and I subtract a positive number, what does my delta G have to be? Is my delta G going to be negative or positive? Right, Wicket? It has to be negative. Does that make sense? It's just math. You cannot take a negative number and then subtract a positive number and not get a negative result. So you're gonna have a negative delta G, guaranteed. Isn't that interesting? So you know what Gibbs would say? Gibbs brought us something so important and so interesting. Gibbs told us that it's pretty much impossible to have a reaction that gets hot and bubbles over and is not spontaneous. It will always be spontaneous. It will always be spontaneous, right? Isn't that neat? So again, a reaction with a negative delta H and a positive delta S is what? Always spontaneous, which means always negative delta G. Isn't that interesting? Do you agree? If you have some time, pause the video, plug in any negative number you want here, and subtract any positive number you want. For instance, you could pause this video, put negative 10. It doesn't matter what the numbers are. It really doesn't. That's why I love explaining in a way without actual numbers, because you can think about the equation instead of just memorizing how to plug in, right? So think about this. Minus 10 minus 90, right? Negative result. Minus 90 minus 10. Negative result. You see? So it doesn't matter what numbers. You could put in minus 1 minus a billion, or you could put minus a billion minus 1. It does not matter what numbers you plug in, because guess what? Any negative value minus a positive value is negative, and that's going to give you a negative delta G. And so what would Gibbs have told us? Gibbs would have told us that, yeah, that's because any reaction that is exothermic and has a negative delta H and has more disorder, has a positive delta S, is always spontaneous. You're always going to have a spontaneous reaction. That makes sense, because a lot of things that happen spontaneously happen to blow up and get hot, right? So that makes sense. It checks out. Let me tell you next the opposite, okay? When is a reaction never spontaneous? Also, before I show you the next example, do you see why I set T to 1? T, it doesn't matter what T is, because T has to be a positive number, right? So it does not matter what T is. T, we could set T to 1, we could set T to 20 billion. It doesn't really matter for the purposes of understanding what I'm talking about right now. It does matter for a different reason, which I'll explain at the end, but it does not matter for our understanding at the moment. Okay, so now let me ask you this. What if I mix two tubes? I mix this chemical and this chemical together, and I notice something weird. It's getting cold. It's starting to feel really cold. What is my delta H? That's right, Wicket. It is a positive delta H. A positive delta H, because it's getting cold to the touch. Now, I look closely at the tube, and not only does it feel cold, it's going from a liquid to a solid, right? It's like things are getting more crystallized and organized. That's weird. So that tells me what? What's my delta S? Yeah, that's right. My delta S has to be negative, because I have less disorder. It's going from a liquid to a solid, or a liquid to a crystal. That's less disorder, not more disorder. So what that means is my delta S is minus, so I'm subtracting a minus delta S. What happens in math when you subtract a negative number, like you're subtracting negative delta S? That's right. When you're subtracting a negative, it's like adding. So in this case, isn't that the same as adding a positive value to a positive value? What does my delta G have to be if I add a positive number to another positive number? What does my delta G have to be? Can it be negative or positive? Positive, right? So my delta G must be positive. Isn't that interesting? So you know, that's what Gibbs would have told us. Gibbs would have told us that, you know, the reason you've never seen two chemicals mixed together getting cold and becoming solid or getting more organized is because that would literally never happen spontaneously, right? So what Gibbs said was any reaction with a positive delta H, which means it's getting cold, it's absorbing heat, it's endothermic, and a negative delta S, right, is never spontaneous. It's never minus delta G. It's always plus delta G, right? So, and that makes sense. I mean, when was the last time you were walking down the street and something spontaneous happened, right? And that thing was getting cold and solid. You know, you've never seen that in real life. And that's because that's not going to happen spontaneously. So isn't that neat? So Gibbs would have told us that, yeah, you're just not going to randomly mix two chemicals in the lab that are getting cold and getting more organized. It just won't happen. Isn't that interesting? Isn't that interesting to understand? All right, now let me give you another scenario. This one's not so cut and dry, okay? What if I mix two chemicals and I feel like, oh, it's getting cold, it's absorbing heat. What would my delta H be? That's right, Wicket. Positive delta H, which means it's absorbing heat. When I mix those two chemicals, it's getting cold. But I noticed that when I added the two, it went from one was a solid, one was a liquid, and then everything became liquid. Everything went from, so one of the solids went into a liquid aqueous environment. Is that more disorder or less disorder? If a solid got dissolved in a liquid, what kind of scenario would that be? More disorder or less disorder? More disorder, right? Because a solid just got dissolved in a liquid, right? So more disorder. Anytime you dissolve something in a liquid and it becomes aqueous, that's more disorder. So my delta S is positive delta S, right? But I need to subtract that positive delta S, right? So I can ignore that sign. So now let me ask you this. What does my delta G have to be? Can my delta G be negative? Can my delta G be negative delta G? Can that happen? Well, let's try this. Let's try this. What if I have plus 10? I'm just making up numbers. Plus 10 minus 100, minus 100. Then what is my delta G? That's right. My delta G is a negative number, right? It's minus 90. Does that make sense? Okay. But think about this for a second. What if my delta H, instead of plus 10, what if my delta H was plus 100 and then I subtracted 10? Now what is my delta G? Is it still a negative 90 delta G? No, now it's actually a positive delta G, isn't it? It's positive 90. Positive 90. Did you follow that? So you see what happened there? If I have a reaction, like I mix two things, and it gets cold to the touch because it's absorbing heat, but it's increasing disorder. You know what that means? That means it could go either way, right? I mean, if this value is really high, then unfortunately, it's not going to be spontaneous. It's going to be a positive delta G. However, if this value is really high, then it will be a spontaneous reaction. It will have a negative delta G. Isn't that interesting? And this is where T plays a role. Remember T, our Kelvin? You ever notice that sometimes you can't get a reaction started until you add some heat? You know, you add some heat to a reaction and then it happens and you're like, oh, it happened. That's why, right? Now we know why T is important, because T can make the weight of delta S even higher, making it more likely to hit negative delta G value, right? So, but you can ignore it for the most part. But now you know some reactions require me to crank up the temperature to get the reaction to go. And now you know why, because that can increase the weight of delta S in those types of reactions. Isn't that interesting? So again, what would Gibbs say? Gibbs would say a chemical reaction with a positive delta H, but also a positive delta S, well, it could go either way, right? It could go either way. So if you have a positive delta H and a positive delta S, well then, I don't know, you would have to figure it out, right? You would have to ask yourself, what's the temperature, right? What's the temperature? What's the value of this? What's the value of that? And then you'd have to determine whether it's spontaneous or not. But it's definitely not always spontaneous, and it's definitely not never spontaneous. And I'll give you an example of one such example. So again, I'll give you an example of a reaction that gets cold to the touch, but because it's driven by, more disorder. You guys ever played sports? If you ever get like a strained shoulder or something, your coach might get you one of those ice packs, but not the ice packs that, the coach grabbed out of the ice bucket. But I'm talking about the ice packs that are warm until you break them. Have you ever seen those ice packs where you have to break the ice pack, then shake the ice pack, and then suddenly it's cold? You ever seen those things? If not, look it up. It's kind of interesting. They have ice packs like that where you have to break something. Now, what's happening inside of that ice pack? There's actually a glass vial of water surrounded by a powder, right? It's like it's a crystal. So when you break the pack, you release the water. The water mixes with the powder and brings the powder into aqueous solution. And when you shake it and mix it, it gets cold. So what happened there in that ice pack? It had a positive delta H because the ice pack got cold to the touch, right? Cold, it's absorbing heat. But did delta S go up or down in that ice pack? Remember, a water got mixed with a powder and brought everything into solution. Is that more delta S or less delta S? That's way more delta S, right? That's a lot of disorder. And if you have a really large disorder, well, yeah, you can make your delta G negative. Isn't that cool? So that's a real life example of what does it mean to have a positive delta H and a positive delta S still be spontaneous in real life. That's a real life example. Isn't that cool? All right, are you ready for the final scenario? Okay, this is the last one, I promise. In this one, what if I mix a couple chemicals and, oh boy, it's getting hot, right? That feels really hot. What is my delta H? Right on cue, Wicket. It is a negative delta H because it's releasing heat, it's exothermic. But I notice not only is it releasing heat, but it's actually crystallizing. It's becoming more orderly. It's less disorder. It's becoming less disordered. It's becoming crystallized inside, or at least a crystalline precipitant is forming and drifting to the bottom. What's my delta S? That's right, less disorder, negative delta S. Great. But remember, I have to subtract that negative delta S. I subtract the negative delta S. So that becomes what? That becomes an addition. Okay. So in this case, in this weird example where I've mixed two chemicals that got hot and started becoming a solid, okay, what happening with my delta G? Well, let's do some thought problems, right? okay, what if my minus delta H is minus 100, okay, minus delta H, let's pretend that's a minus 100 value, but my delta S is 10, right, positive 10. In that case, it would be minus 100 plus 10, which is what? That would give me a minus 90 or a negative delta G. That would be a spontaneous reaction, right? So does that mean that these types of things are always spontaneous? Well, not necessarily. Let's think about this. Let's flip those numbers around. Just flip them for fun. If my negative value, negative delta H, was minus 10, but my delta S value was bigger, it was plus 100, now what happens to my overall G value? Now it's a positive 90, right? It's positive 90, so it's a positive delta G. So just like the previous example we just finished, remember the ice pack example? If you have a negative delta H and a negative delta S, again, you don't know what the outcome's gonna be. Now it's important to look at what your temperature is. Now it's important to know the value of delta S, the value of delta H, to see if that's gonna give you a negative outcome, right? And it may not, right? So isn't that interesting how you can derive such fundamental properties of life from a simple arithmetic equation like this? Thanks, Gibbs. This is very, very interesting, isn't it? And by the way, for you really advanced, really with it, students who are just right up to speed with everything I'm saying, you might be curious, like, why is this working? What's driving this? Entropy drives all of this. Entropy drives all of this. For example, delta H is essentially entropy. It's not disorder, S, but it's a type of disorder, isn't it? Because if something's releasing heat, it's going to have a negative delta H. It's releasing disorder. It's releasing disorder. If you're releasing a bunch of heat, you're releasing a bunch of disorder, you're going to have a negative delta H, which is going to help you to drive that reaction forward. Conversely, if you are making more disorder by blowing up or turning into gas or falling apart or whatever, if you're making tons of disorder, you're going to have a positive value here, which is going to drive the reaction forward. So either way, this equation is driven by disorder to give you a spontaneous reaction. Either the disorder of releasing heat or the disorder of actual disorder. Okay, so again, if you don't understand this stuff, no worries, go over it a few times, do some examples, read your textbook, you can do it. I know thermodynamics is hard, but hopefully this made some sense and made better sense of what Gibbs was trying to tell us. All right, welcome back from the board. Now, another word for spontaneous or negative delta G is an exergonic reaction, an energy outward reaction. Exergonic reactions proceed with the net release of free energy to the surroundings. So again, instead of saying a negative delta G reaction or a spontaneous reaction, we can refer to it as an exergonic reaction. Conversely, an endergonic reaction, it's essentially a positive delta G reaction. It's a reaction which requires energy. It absorbs energy from the surroundings. So here you can see both of these laid out in these graphs, these bar graphs. On the left, you have reactants, and on the right, you have products. The y-axis is showing you free energy. Remember, the value is G, right? The units of G. So these reactants have a higher G value, and the products seem like they have a lower G value. And on the x-axis, you have the progress of the reaction from reactants to products. This looks like a reaction where you start with a higher G value and you end with a lower G value. Is this a negative delta G reaction or a positive delta G reaction? That's right, Wicket. This is a negative delta G reaction, right? Because you're starting with a high free energy state You're ending this process with a lower free energy state. So this is a negative change in G, right? So it's a negative delta G. That means that this is an example of an exergonic reaction, a spontaneous reaction. And what did I tell you happens during a spontaneous reaction? Energy is released, not required, released, okay? So again, during an exergonic reaction, the reactants have a higher free energy, higher G value. The products have a lower free energy or lower G value. That means they have a negative delta G, which releases energy. Okay, and these are known as spontaneous processes. Conversely, look at an endergonic reaction, right? An endergonic reaction. Here, the reactants begin with a low G value, and the products have a high G value. So this means that the change in G is from low to high. That means that the delta G is positive. It's a positive delta G reaction. It's an endergonic reaction. That means it's a non-spontaneous reaction. And that means that this reaction will not occur. It will not occur without energy input, right? You're putting energy into the system to make this reaction occur, to drive this reaction forward. All right, so I hope that made some sense. Now again, I stated this before, but I just wanted to drive home this concept that recall that a term spontaneous, so negative delta G, means that the reaction is energetically favorable. It does not mean that it will occur rapidly. So spontaneous, when it comes to thermodynamics, does not mean quickly. It just means it will proceed without energy input. Spontaneous processes could be instantaneous. They could be super fast, but they could also be very, very slow. So for example, you know how rust occurs on your car? If you have too much moisture and you're driving your car and you get too much moisture on your car, that can cause rust to form on your car. And it could take 20 years for your car to rust, but that's still a spontaneous reaction. Does that make sense? So just because something is happening slowly doesn't mean it's not a spontaneous process, as long as it's energetically favorable, as long as it's negative delta G. Now remember what I mentioned equilibrium means? In thermodynamics, equilibrium is when delta G equals 0. No work is being done. Reactions in a closed system, such as an isolated hydroelectric system, eventually reach equilibrium and can do no work. So you see here, this is a closed system, a hydroelectric system, where the water is high on one side, and that is giving this water a high potential energy on the left side. That water can convert its potential energy into kinetic energy as it drifts down to the other container. And this kinetic energy of water can drive a turbine. And this turbine can turn to produce electricity to light this light bulb. Now, because it's a closed system, you can reach equilibrium quite easily. When the water levels out, there's no more potential energy on the left side to convert to kinetic energy towards the right side to power this hydroelectric system. And so the system will achieve delta G equals 0, will reach equilibrium. However, in an open thermodynamic system, like this open hydroelectric system, you're not going to reach equilibrium, right? As long as water is coming in, that's going to raise the water level on the left side, providing potential energy, which will flow to the right side to turn the turbine and turn the light on, right? So in an open system, you can maintain a negative delta G that is net negative. And so what you should remember is that organisms like you and me are open thermodynamic systems. Much like this open thermodynamic hydroelectric system right here on this slide, as long as we get water, as long as we get food, sugar, fats, as long as we get nutrition, we can continue functioning, and our cells can continue functioning and not reach equilibrium. But keep in mind that inside of our cells, we have metabolic processes, right? Metabolism, which converts one type of molecule to another, to another, to another. So in our bodies, it's more like, I would say, more like this hydroelectric open system than the previous one, because of the numerous metabolic pathways that occur inside of each and every one of our cells. Again, your cells want to do work. And there are three kinds of work that cells want to accomplish: chemical work, transport work, and mechanical work. Either way, these are positive delta G processes that require energy. And do you guys remember in grade school or in high school, how do cells get their energy? What is the energy currency of a cell? That's right, Wicket. ATP. You may have heard of ATP in the past. ATP is the energy currency of the cell. You can think of it as the batteries of a cell. ATP powers cellular work by coupling exergonic reactions to endergonic reactions. I'll explain what that means in a minute. But first, let's look at the structure of ATP. Let's look at what makes ATP so special. So ATP, or adenosine triphosphate, is composed of a ribose. Remember, ribose is C5H10O5. It's a 5-carbon sugar. It's a pentose sugar. As well as the nitrogenous base, adenine, a nitrogenous base, and 3 phosphate groups. In addition to energy coupling, yes, ATP is a nucleotide. It's a nucleotide triphosphate that functions as one of the nucleoside triphosphates used to make RNA. So this is really surprising to a lot of students, that you've heard of ATP in the past and you know that ATP is the energy currency of the cell. But did you know that the cell has two choices for what to do with ATP? It can either make RNA with ATP, or it can use ATP as energy currency in the cell. So that's kind of neat, right? There's two functions for ATP, not just energy, but also you could use it as the A's in RNA, right? RNA uses A's, G's, C's, and U's. Remember that? Well, the A's are ATP. It's just really interesting to understand that concept. But again, what makes ATP a nice high energy molecule? Let's talk about that next. So this is what ATP looks like. This should look very familiar to you after, our chapter on biomolecules. Do you remember? ATP looks just like a nucleotide, but instead it's called a nucleotide triphosphate, right? So you have 3 phosphate groups. So it's a nucleotide triphosphate, and it's A for adenine. So it's adenine or adenosine triphosphate. This here, let's start with this here. Remember this mustard colored structure? This is a nitrogenous base, and this happens to be the purine with 2 rings, adenine. Next, down here, you have the pentose sugar. Remember the pentose sugar, the 5-carbon sugar, ribose, right? And yes, ribose is the sugar for RNA, not for DNA. And then you have your 1, 2, 3 phosphate groups, so triphosphate. So it really is a nucleotide, but with 3 phosphate groups. And this is a high energy molecule. Now remember high energy molecules, this is chemical energy. And I want you to remember something. Chemical energy is a form of potential energy. Now, let me ask you this to quiz you. Is this molecule, ATP, is it a type of potential energy because of the location of this molecule or because of the structure of this molecule? What makes it potential energy? That is right, Wicket. This is high potential energy due to its structure, okay? It's the structure of this molecule that gives it high chemical and potential energy. Let me explain why. Look at the answer lies mainly in these 3 phosphate groups. Let's look at these 3 phosphate groups closely. What do phosphate groups, what property do they have? What is this right here? Do you recall when we learned about the phosphate functional group? We learned that they're negatively charged, right? So these phosphate groups have a negative charge. Do you think that negative charges want to be this close to one another? Okay, look how close these negative charges are. What do we know about like charges and being close to one another? Do you think they want to be close? No, right? So what would you say would happen if I came along and I were to attack this bond right here with this oxygen? What if I could attack that with water and hydrolyze that bond, right? So let's say I try to cut this terminal phosphate. Terminal phosphate means the last phosphate. What if I tried to cut that off with water by hydrolysis? Do you think this phosphate group would hang out, or do you think it would be more than happy to jet out of there and get away from this other negative charge? That's right. It would be more than happy to get out of there. The negative charges do not want to be anywhere near each other. If I were to hydrolyze this bond right here, this phosphate group would leave with joy. Okay, and so it really is, it reminds me of magnets. You guys know, you ever played with magnets? Let me go grab some magnets and show you something that might help with your understanding. All right, I found them. These are some magnets I have laying around the house. You guys have all messed with magnets, I'm sure. As you know, there's a side where they snap together quite tightly, but as you all know, when you flip a magnet around, they repel, right? And it's actually quite difficult to get them to come together, and that's due to repulsion. Now, think of ATP like this, right? Think of the phosphate groups of ATP as magnets that are the wrong way around. All of these phosphate groups, they're just wanting to get away from one another. So when you hydrolyze this bond and cut that bond, this phosphate group goes flinging off, just like these magnets would want to go flinging off, right? So you see, these magnets, if I try to push them together and hold them together, that's not going to work for very long before they, fly apart, right? And they fly apart. And that's because when I push them together, that's a high potential energy based on the structure of that orientation. So you can think of this ATP molecule as chemical energy due to structural potential energy based on these phosphate groups being so close to one another, such as when this terminal phosphate is cleaved or hydrolyzed, this phosphate group leaves with a big release in energy. So again, energy is released from ATP when that terminal phosphate, that means that third phosphate, the terminal phosphate bond is broken by hydrolysis, the addition of water. The energy does not come from the phosphate bonds, but from the chemical change to a state of lower free energy of the products. The fact that phosphate group leaves with such tenacity, that's what causes the release of energy. And here you can see what I've been talking about. Here you have adenosine triphosphate, or ATP. Upon hydrolysis, so water cleaving the terminal phosphate, that terminal phosphate leaves, providing an immense amount of energy, or ATP. So this is a spontaneous process. This is a process that releases energy. This would have a negative delta G. It releases energy. And this is how cells power endergonic processes in the cell. When the cell wants to move something around, it can use this energy. When the cell wants to transport things out of the cell against the concentration, it can use this energy. If the cell wants to create a chemical or make something that requires energy, it can use this energy. So this is the energy that the cells use in order to do things that require work. And by the way, I just want to point out one more thing before we take a break time with Gizmo and Wicket. I want to show you this phosphate group. See how it's all by itself now? It's lonely over here all by himself. Well, this phosphate group is now called Pi, and I want to tell you why. Pi stands for inorganic phosphate. Do you remember what organic means? It means connected to a carbon and a hydrogen, right? You have to have a carbon and a hydrogen to be organic. So look, these phosphate groups are called organic phosphates. You know why? Because these phosphate groups are connected to an organic molecule. The rest of this adenosine and the sugar, right? This is an organic molecule with a lot of carbons and hydrogens. Does that make sense? So because these phosphate groups are connected to that organic molecule, these are known as organic phosphates. However, upon hydrolysis, this phosphate group, remember, it's comprised of only a phosphorus and 4 oxygens, right? So it is no longer connected to any carbons or hydrogens. So it is called inorganic phosphate. Now, knowing all that, let's go ahead and take our break time with Gizmo and Wicket and see what these little guys are up to, and we'll be right back to do the latter half of this chapter. All right, welcome back from break time with Gizmo and Wicket. Let's get started. So again, cellular work. When the cell wants to perform work that requires energy, be it mechanical, transport, chemical work, this is all powered by ATP hydrolysis. When the ATP is hydrolyzed, that energy is used to drive the endergonic reactions. So overall, the coupled reactions are exergonic. Let me show you an example. Okay, here, look at this example from your book. Here, the cell is wanting to produce this amino acid named glutamine. It's one of the 20 naturally occurring amino acids, glutamine. Now, the way the cell produces glutamine is by combining glutamic acid and ammonia. By joining the two together, the cell is able to make glutamine, which is an amino acid it needs in order to make proteins. Okay, this is just one example of an endergonic process that the book selected out of thousands and thousands and thousands of examples that it could have selected. So don't get bogged down in, what is glutamate or what's glutamic acid. Just follow the idea here, right? So again, the cell wants to create this molecule and it needs to combine these two molecules. But look at the energetics of this reaction. It says that this reaction is a positive delta G reaction. It has a positive kcal per mole. That means it is a positive delta G. What do we know about reactions with a positive delta G? Are those spontaneous or non-spontaneous? That's right, Wicket. Non-spontaneous, right? So if the cell is to make glutamine, it's going to need energy to do that. It's going to need some energy. Otherwise, without some source of energy, the cell's not going to be able to make glutamine. Does that make sense? So where can we find energy? Remember, we could use ATP. Here we go. Let's use the ATP. If we use ATP to phosphorylate glutamic acid, that means when you cleave ATP, you give the terminal phosphate to glutamic acid. This forms a glutamic acid, which has a phosphate group attached. This is known as a phosphorylated glutamic acid, or in general, a phosphorylated intermediate. This would allow the ammonia to then bind to the glutamic acid to form glutamine. So this is known as a phosphorylated intermediate. And this is one technique by which a cell can use ATP in order to produce a product that it otherwise would not be able to produce. And the way this is happening, you can think of it just energetically. Let's just talk about energetics. Remember, to produce glutamine, to produce this amino acid glutamine, this required a positive delta G reaction. It required an endergonic reaction of combining glutamic acid and ammonia. The energy for that was provided by cleavage of ATP, hydrolysis of ATP. ATP releases 7.3 kcal per mole of energy. The reaction for making glutamate only required 3.4 kcal per mole of energy. So if we do the math here on this left box, you can see that we provided 7.3 kcal per mole of energy. The process only required 3.4 kcal per mole of energy. We can get that done and have extra energy to spare. By the way, that extra energy usually leaves as heat. But you can see what the benefit of having ATP lying around is, right? By having ATP lying around, anytime the cell wants to do work, such as make glutamine, which requires energy, it can cleave an ATP molecule and use that energy that's released to provide the energy to do the work. This is known as energy coupling. When an exergonic reaction, such as cleaving ATP, releases energy, and you use that energy to drive an endergonic reaction, like making glutamate, this is known as energy coupling because you're coupling the energy released from an exergonic reaction to drive an endergonic reaction. And also, transport and mechanical work in the cell are also nearly always powered by ATP hydrolysis. The use of ATP is the most common way that a cell can obtain the energy it needs to do work. Okay, so you can see here transport work. This is a transport protein, a carrier protein. This looks like an active pump or an active carrier. It can use ATP to pump solute against the concentration gradient. So for example, if you want to do active transport of solute, you could use ATP to drive the solute. What about mechanical work? You remember these little walking feet that we talked about? These little walking feet that walk along microtubules, these motor proteins? They can use ATP as well. So you hydrolyze an ATP, and this can allow the next step to take place. And later on, we're going to learn about how ATP is regenerated. So this is a reversible reaction. Just like ATP is cleaved into ADP, by the way, when you cleave ATP, you're left with ADP, D standing for diphosphate. So adenosine diphosphate has 2 phosphate groups. Adenosine triphosphate has 3 phosphate groups. This is a reversible reaction. You cleave ATP to harness the energy to do work. But then later on, remember the mitochondria, which they say is the powerhouse of the cell? The mitochondria's job is to combine a phosphate group and ADP to replenish ATP, to make ATP again. We're going to learn about that. That's called cellular respiration. And we're going to learn about that in a subsequent chapter. When ATP is hydrolyzed, this releases energy used by the cell to do work. Any kind of endergonic energy-consuming process can be powered from the energy released by ATP hydrolysis. But then it's the mitochondria's job to add the phosphate groups, the inorganic phosphate and ADP together to reform ATP. And this is energy from catabolism that drives this process. Catabolism drives ATP production. Anabolism drives ATP breakdown. So now let's introduce this concept of enzymes and how enzymes speed up metabolic reactions. So we talked about spontaneous reactions, and I told you that spontaneous reactions can occur quickly or slowly, as long as it happens in an energetically favorable way, so in a negative delta G way. Spontaneous reactions do not need added energy, but they can be so slow that it's imperceivable. For example, the hydrolysis of sucrose. Do you guys remember sucrose? It's a disaccharide of glucose and fructose held together by a glycosidic bond. Well, sucrose can break down or hydrolyze into the monosaccharides glucose and fructose spontaneously. But this could take very long to do. So how long? At room temperature, a solution of sucrose in sterile water would sit for years without appreciable hydrolysis. So any appreciable hydrolysis occurring. So just because a reaction is spontaneous does not mean it's going to happen anytime soon. So if you want to speed up these reactions, you can use enzymes. That's where enzymes shine. Enzymes speed up the rate of a reaction. Enzymes serve as a catalyst. A catalyst is a chemical agent that speeds up a reaction without being consumed by the reaction. This means that catalysts can not only speed up a reaction, but they can do it over and over and over again without getting destroyed or used up. An enzyme is a macromolecule, which is typically a protein. Okay, most enzymes are proteins that act as a catalyst. So these are proteins that are catalysts. They speed up a specific reaction without becoming consumed by the reaction. So for example, adding the enzyme sucrase, and by the way, enzymes usually end in ase, A-S-E. So anytime you see a word that ends in A-S-E, you should be aware that it's most likely an enzyme. So sucrase is the enzyme that breaks down sucrose solution at room temperature. It will catalyze the complete hydrolysis of sucrose within seconds. So did you see what happened? If you add sucrose to water, it can take forever to break down. It could take a long time to break down. But if you add the enzyme sucrase, which breaks down the solute sucrose, well, then you can speed up that reaction significantly and just to a fraction of the time. So here you can see that reaction taking place. In purple, you have the enzyme sucrase. In green, you have the disaccharide, which is its solute. Okay, it's a substrate, I should say. Enzymes act on substrates. This sucrose is the substrate for sucrase, the enzyme. So sucrase binds to its substrate, sucrose, and with the help of water, what do you think the water can do? The water will attack the glycosidic bond. Remember that water hydrolyzes bonds, right? Water can attack the glycosidic bond and free the two monosaccharides from one another. And now you've broken sucrose, the disaccharide, into glucose and fructose, the monosaccharides. And look here, the water molecule is now distributed among them. A hydroxyl group from the water is attached to glucose, and a hydrogen is attached to fructose. You have used sucrase to speed up the breakdown of sucrose. And the way enzymes accomplish this is by manipulating this factor. Let's talk about activation energy. The initial energy needed to break the bonds of the reactants, so for example, of sucrose, is called the activation energy, EA. Okay, the activation energy. Heat in the form of thermal energy absorbed from the surroundings is often what supplies activation energy. Have you ever noticed that sometimes all you have to do is heat something up and that gets it to, react or do the chemical process? Well, that's because heat is often what's used to speed up reactions. However, you can also use enzymes to speed up reactions. Okay, molecules become unstable when enough energy is absorbed to break bonds. This is the transition state, and that's the state that the enzyme helps the molecules to achieve. So here you can see reactants will absorb some energy to reach what's known activation energy, the initial energy needed to start a reaction. This allows these molecules to reach their transition state and rearrange their bonds, forming more stable products and lower free energy products. So this is an example of an exergonic reaction. However, the speed bump in the middle is what's known as activation energy, the initial energy needed to achieve a chemical reaction, to push a chemical reaction forward. So the activation energy provides a barrier that determines the rate of a spontaneous reaction. So think about it this way. The bigger the speed bump, the bigger the activation energy, the slower the reaction. And the lower the speed bump, the lower the activation energy, the faster the reaction. So let me ask you this. If the activation energy was very tiny, almost indistinguishable, like negligible, tiny little speed bump, what would that tell you about the reaction? That's right, Wicket. If the activation energy is very, very, very low, that would be an instantaneous reaction. That would be a reaction that happens instantaneously. Exactly right. So the difference between an instant chemical reaction or an instant spontaneous reaction and a spontaneous reaction that takes 20 years is simply the height of this activation energy speed bump, right? The initial energy required to push a reaction forward. And again, the activation energy provides a barrier that determines the rate of a spontaneous reaction. For some reactions, the activation energy is low enough that even thermal energy, just heat from the room, is sufficient to overcome the activation energy barrier. Most reactions, on the other hand, have a high activation energy and need additional energy, usually heat, to reach a transition state. However, adding heat is not a useful way to speed reactions in cells because it can cause proteins to denature. You know, we're not applying heat in our cells to make things go, to provide an activation energy. Instead, we use what are called enzymes, right? Enzymes. Instead, organisms carry out catalysis, the process by which a catalyst selectively speeds up a reaction without being consumed itself. We use enzymes to speed up reactions. We do not use temperature or heat to speed up reactions. It wouldn't be practical inside of our cells. An enzyme catalyzes a reaction by lowering the activation energy barrier and for the reaction to occur at a moderate temperature. An enzyme cannot change the delta G of a reaction. So it doesn't change the delta G from negative to positive. It only speeds up a reaction that would have eventually occurred anyway. Does that make sense? Enzymes speed up reactions that were going to happen anyway. Reactions that have a negative delta G. What enzymes do is they effectively lower the activation energy such that these processes can occur at body temperature or room temperature. And that's how enzymes function. So here you can see a reaction where the reactants have a high G value. Up here, free energy is G value. And the products have a low G value on the right. So what kind of process is this? Is this a spontaneous process or a non-spontaneous process? If the reactants start with a high G value and the products have a low G value, is this a positive delta G reaction or a negative delta G reaction? That's right, Wicket. They have a negative delta G, right? Because you start with a high G value, you end with a low G value. That's a negative delta G. This is a spontaneous reaction. However, what is this speed bump right here? Why is there a speed bump here? Why doesn't it just go from reactants down to products? Well, remember, this is the initial energy needed to start a chemical reaction. This is known as EA, or activation energy. And in black, look at this. This is the massive speed bump you have without an enzyme present, without an enzyme catalyst present. However, when you add an enzyme catalyst, look what it does to that speed bump. Look what it does to the activation energy. It lowers it substantially, right? So now you have a much lower hurdle to cross, a much lower energetic barrier. And so and remember, anytime you lower a speed bump, remember you could drive over it faster, okay? That speeds up the reaction. And that's exactly what enzymes do. Enzymes lower the activation energy, thereby speeding up the reaction. Again, keep in mind some terminology associated with enzymes. Enzymes usually end in the suffix ase, A-S-E. Enzymes act on a substrate. This is the reactant that the enzyme acts on. So for example, the enzyme sucrase would have this substrate sucrose. The enzyme binds to the substrate, forming what's known as an enzyme-substrate complex. Oh, hi, Wicket. Wicket's come to say hi again, everybody. Hello, Wicket. Love you too. While bound, the catalytic activity of the enzyme converts substrate to product. So here, let's take a look at what we're talking about. So here's an illustration of what I was talking about. Remember, enzymes are proteins, and this here in blue is your protein enzyme. Let's pretend this is sucrase, the enzyme that breaks down sucrose. So let's pretend this is a protein. Now, I want you to remember something. Proteins, remember when we learned about proteins? I told you that it's so important that you remember that proteins need to fold correctly in order to function correctly, right? So you see how this protein is folded nicely like this into this tertiary structure? Well, that's super important to the function of this protein. So if this is an enzyme, well, yeah, just like any protein, it has to fold just right into the proper tertiary structure in order to function. Does that make sense? Because look at this. When this protein is folded, it forms this nice, perfect little pocket called an active site. And that active site is perfectly shaped to accommodate the substrate. So again, if this was, if this was sucrase, the enzyme, this substrate, this little molecule would be sucrose, its substrate. I'm just making stuff up, but you get the point. This is sucrose. This would be sucrase. Well, guess what? That substrate will find its way into the active site. And let me tell you guys something. Enzymes are so specific for what they will bind to. Again, remember, enzymes, if this is the enzyme for sucrose, it will only accommodate sucrose. No other enzyme, no other substrate would go into this pocket, right? So if it's maltose, the disaccharide, it won't be accommodated by this active site. If it's lactose, it won't go into the active site. It would have to be sucrose. Does that make sense? Each enzyme is specific for its particular substrate, a very specific substrate. And once the substrate finds its way into the active site, there's what's known as an induced fit. Induced fit, notice how the enzyme kind of hugs the substrate in place, right? It kind of wrapped over the substrate, locking it in place. That's called the induced fit. And now you have what's known as the enzyme-substrate complex, and that's where the magic happens. Okay, there's going to be catalysis. There's going to be a speed up of the breakdown of this substrate, for instance. So again, how did it work? The substrate or substrates enter the active site. Remember the active site of the enzyme. The substrates are held in active site by weak interactions such as hydrogen bonds. The active site lowers the activation energy. This allows the substrates to be converted to products. The products are released, and then the active site is available for the enzyme to do this again and again and again. Remember, enzymes are not consumed by the reaction that they catalyze, right? Enzymes can do this cycle over and over and over again. But at this point, that's very hand-wavy, right? That's very vague. You might be saying, but Dr. D, what in the world does lowering the EA mean? What does lowering activation energy even mean? And what does that look like? Like, can you give me a concrete example of lowering EA? What does that even mean? Well, there are. Let me give you some examples of what exactly is meant when we say an enzyme lowers the activation energy. In fact, this can be done in a number of ways. Here's a variety of mechanisms that enzymes lower EA. For example, the enzyme might make substrates oriented to facilitate the reaction. So the substrate might be oriented a particular way to facilitate the chemical reaction, the catalysis. The substrates may be stretched to make the bonds easier to break. The active site may provide a microenvironment that favors the reaction, such as an acidic microenvironment or a basic microenvironment. Amino acids in the active site may participate in the reaction. So you see, these are the 4 concrete ways by which enzymes lower activation energy. Now, again, remember that enzymes are usually proteins, and proteins must be folded just right into that tertiary structure in order to function. However, what happens when we mess with that poor enzyme? So enzyme activity can be affected by general environmental factors such as temperature and pH. What if I boiled my enzyme? Do you think it's going to hold up? Its tertiary structure is going to hold up? Or do you think it's going to denature? It's going to denature, right? Well, what if I put my enzyme in an acid, a really strong acid, when it's not meant to, exist in that environment? Well, that might denature my protein, right? Well, think about it. Temperature and pH can cause my protein to function poorly, if at all. It might cause my protein to denature, unfold, right? And remember, once a protein is unfolded or denatured, it doesn't typically renature, right? And so you've lost functionality. What's interesting about enzymes is that each enzyme has an optimal temperature at which it catalyzes its reaction. So in your body, most of those enzymes prefer body temperature, right? About 37 degrees C. But did you know there are some archaea that live in boiling springs, hot springs that are about 100 degrees C? And those enzymes, the archaeal enzymes have to work at 100 degrees C. So just because your enzymes in your body prefer a certain temperature for optimal activity doesn't mean all enzymes work at the same temperature and are optimal at the same temperature. So, and remember what happens when you go above our required temperature for the enzyme or optimal temperature for our enzyme. At some point, the enzyme begins to denature because it becomes too hot, and that protein then loses function. That enzyme will lose function. And again, in your body's temperature is about 37 degrees C, 37 degrees Celsius. So the enzymes in your body work best in that range between 30 and 40 degrees Celsius. Whereas, like I said, those thermophilic bacteria and archaea that live in hot springs, for instance, they can withstand upwards of 75 degrees C or more. See here, again, this would be the rate of reaction for enzymes in a human body reaching optimal activity at about body temperature, 37 degrees. Whereas look at the optimal enzyme temperature for one of these thermophilic or heat-loving bacteria or archaea, it would be much, much higher. In fact, if you took one of these bacteria out of their sulfur spring environment and brought them to our environment, they would actually freeze. They would not be able to even move or function. Isn't that interesting? Same thing with pH. Not all enzymes prefer the same pH for optimal activity. Did you guys see with your peroxidase lab that you did? If you did the peroxidase lab, pH 5 was the optimal pH for peroxidase activity. But that doesn't mean all enzymes work at best at pH 5. What about in your stomach? You know your stomach has stomach enzymes, digestive enzymes in your stomach. But your stomach is about pH 2, right? Your stomach has a pH of 2. Well, guess what? The enzymes that work in your pH 2 stomach, like pepsin, those enzymes fold best and function best optimally at pH 2. Whereas optimal pH for trypsin, which is an intestinal enzyme, remember your intestines are further away from your stomach. They are not in an acidic environment, are they? So the enzymes like trypsin in your intestines, they function best at pH 8. However, the enzymes from your stomach where it's very acidic, like pepsin, they function best at pH 2. So what is our takeaway here? I just want to give you an understanding. So what you should understand is different enzymes have different optimal pH as well as optimal temperature. Just because your enzymes in most of your body prefer a particular temperature or pH does not mean that all enzymes are equal. It does not mean that all enzymes prefer the same exact conditions for optimal performance. Okay, again, look at this. Your stomach enzyme pepsin works best at pH 2 because your stomach is at pH 2. Whereas your intestinal enzyme trypsin, another digestive enzyme, works best at pH 8. So we can't say that all enzymes function best at the same pH, and we can't say that all enzymes function best at the same temperature. That's just not true. Now, some enzymes require non-protein helpers called cofactors for help. These non-protein helpers bind to the enzyme permanently or sometimes reversibly with the substrate. And these cofactors allow the enzyme to work correctly. Now, most enzymes work just fine once they are folded into their tertiary state. However, some enzymes and some proteins require helpers in order to function correctly. These helpers are called cofactors. Cofactors are non-protein helpers that bind to the enzyme, sometimes permanently, sometimes reversibly, along with the substrate. Inorganic cofactors include the elements. So there are a host of inorganic cofactors. For example, zinc is an inorganic cofactor. Iron is an inorganic cofactor. Copper, is an inorganic cofactor. In fact, in your diet, have you ever heard of vitamins and minerals in your diet? Well, when they say minerals, like you need to get your minerals in your diet or from some kind of multivitamin, you know how you need your minerals? Well, minerals serve as cofactors. This is why you need them in your diet. Isn't that interesting? So, for example, let me give you an example of one of these inorganic cofactors. Remember we talked about hemoglobin, and it's a very important protein. It's a quaternary structure, a protein complex in your blood, remember? And it carries oxygen in your blood. It carries oxygen throughout your body. Well, what inorganic cofactor do you think your hemoglobin proteins depend on as cofactors? That's right, Wicket. Iron, right? You all heard you have iron in your blood, right? Well, iron happens to be an inorganic cofactor that binds to hemoglobin, allowing it to carry oxygen properly, right? But iron's not the only cofactor. Your thyroid has enzymes that require iodine. You've got zinc. Zinc is important in the nucleus for certain proteins that bind to DNA. You need copper in your diet. You need magnesium and manganese and cobalt. I mean, there are a host of different minerals that you need in your diet because different enzymes require different cofactors. For instance, calcium might be a cofactor for a protein, right? You know how you have calcium in milk? Well, calcium is a cofactor. Isn't that interesting? Different elements are required for proper function of different proteins. But again, not all proteins require a cofactor. Now, there are organic cofactors as well. Remember, organic means contains carbon and at least one hydrogen. But the organic cofactors are called coenzymes. And the coenzymes include vitamins. Vitamins. You've heard of vitamins, right? Vitamins are organic cofactors. So vitamins are very similar to these elements in that certain vitamins are required for different enzymes to work properly. Some enzymes might require vitamin C binding to them to function correctly. Some might require one of the vitamin Bs to attach to function correctly, or vitamin D or vitamin E. The vitamins serve as cofactors. The vitamin will bind to the enzyme or the protein, allowing it to function correctly. Isn't that interesting? And a lot of times these cofactors are found in the active site, but not always. But often the cofactors are found in the active site of the enzymes. All right, isn't that cool? So now you understand why you need vitamins and minerals in your diet. Because if you become deficient in any inorganic cofactor or organic cofactor, vitamin, well then you may not have that enzyme function correctly, and then you may have health issues associated with a deficiency in that cofactor. Isn't that neat? Now you know why the vitamins and minerals are important. Now, just like cofactors help enzymes function, inhibitors hinder or inhibit protein function and enzyme function. So what is an inhibitor? An inhibitor is a chemical that selectively inhibits the action of specific enzymes or proteins. If an inhibitor forms a covalent bond with the enzyme, then the inhibition is irreversible. It's a permanently hindered enzyme. However, many inhibitors bind to the enzyme by weak interactions, resulting in a reversible inhibition. So it all depends on the inhibitor. Some inhibitors will permanently take out an enzyme. Some inhibitors will temporarily take out an enzyme. Now, there are different types of inhibitors. Competitive inhibitors are ones that closely resemble the substrate to the point where they can actually get into the active site and compete for the active site. So let me show you. Let's pretend this in purple is the enzyme, right? This is the enzyme. And here is the enzyme substrate in teal. And then this is the active site, right? The active site which accommodates the substrate. That's normal, right? But a competitive inhibitor mimics the substrate, but it is not the substrate, right? It's just an inhibitor. Notice what the inhibitor did. It kind of got in there and blocked access to the normal substrate. Now the normal substrate can't bind, and that's why it's called a competitive inhibitor. This small molecule competes for the active site with the regular substrate. However, this inhibitor cannot be broken down by the enzyme. It just gets in there and gums up everything and slows everything down and prevents the enzyme from doing its job, right? So competitive inhibitors work by competing for the active site. By doing what? By mimicking the substrate, the true substrate. Now, non-competitive inhibitors, they kind of work in a different way. They bind to a different part of the enzyme, not the active site, but they still have this inhibitory effect on the enzyme. So let's see how this occurs. So here you have the non-competitive inhibitor. it's binding way over here. It's binding to this bottom portion of the enzyme. However, it's still causing problems with the active site. It's still causing problems up here. Now, some types of inhibitors you should know about are toxins and poisons. These are often irreversible enzyme inhibitors. Now, here's an important concept to understand with regard to enzymes, and this is the concept of allosteric regulation. Allosteric regulation occurs when a regulatory molecule binds to a protein at one site and affects the protein's function at another site. So, did you see when we talked about non-competitive inhibitors? They kind of work in an allosteric way. They bind to an enzyme at one site, but have an effect at another site. Isn't that interesting? And the reason that works, I think Wicket's back here exploring. Check him out. He's up here exploring the reason allosteric regulation works is because, remember, a protein is this properly folded thing. And just because... Yes, Wicket, what happened, buddy? What is it, buddy? That was a sad meow. Oh, Wicket's telling me to take a break, you guys. Wicket, what is it, buddy? Is it snack time? Sometimes you have to take a break with Wicket. Wicket's here to tell us we need a break, a little break time. All right, Wicket, I'm almost done. Snack time soon. Yeah. Did you hear him? He was, yeah. Wicket, you're such a personality. All right. So anyway, look at this allosteric regulation, right? If something binds to this part of the protein, it can actually cause the rest of the protein to kind of misfold. Because remember, proteins are these intricately folded things, right? And it's all one long string of amino acids that folded into this perfect little origami, right? This perfect little tertiary structure. If I mess with this part of the protein, I could change that part, right? Because it's all interconnected. Does that make sense? So the way non-competitive inhibitors work is via allosteric regulation. They bind here, but they can have effects over there because it's all interconnected. Now, the final concept of the chapter, we've reached the end of this chapter, chapter 8, is feedback inhibition. So what is feedback inhibition? It is when the end product of a metabolic pathway shuts down that very pathway. Feedback inhibition prevents the cell from wasting chemical resources by synthesizing more product than is needed. So let me show you how this works. It sounds fancy, but it's actually quite straightforward. I want to show you something. First, I'm going to show you what this initial substrate is. This is the initial substrate. This substrate is threonine. And by the way, this is one example your book pulled of tens of thousands of different examples that it could have chosen. But it chose this one. Okay, so the identity of this original substrate and this final end product, their identity is not so important as the concept, right? So try to understand the concept, but bear with me. Let's say I have this substance here in blue, right? This is my substrate, my initial substrate in blue. This is threonine. Do you know what threonine is? It's one of the 20 naturally occurring amino acids, okay? This is an important resource for the cell, isn't it? Doesn't the cell need threonine around? So the cell needs this amino acid because it wants to make proteins, and it's going to use these amino acids to make proteins. However, the cell also needs this amino acid as well. Look at the end product. The end product of this metabolic pathway is this red product called isoleucine. That's another one of the 20 amino acids. So isoleucine is one of the 20 amino acids, where threonine is one of the 20 amino acids. Would you agree that the cell requires both threonine as well as isoleucine? You can't you can't do with just one, right? Don't you need both of these substances in order to build proteins and grow as a normal cell? But here's the thing. The only way the cell can make this amino acid is by converting this amino acid to isoleucine, okay? And the way you do that is through a metabolic pathway. Remember how that works? The initial substrate threonine, the blue thing, is converted by enzyme 1 into intermediate A, then enzyme 2 converts A into B, and then enzyme 3 converts B into C, and then enzyme 4 converts C into D, and then enzyme 5 comes along at the end of the metabolic pathway, converting intermediate D into the end product, isoleucine. And that's great, right? Now we have isoleucine. But here's the thing. Let me explain. Do you remember what we said earlier? Enzymes work at a constant rate, right? Enzymes work at a constant rate, and they do not get consumed by the reaction. So what that means is these enzymes, if you let them, they would just convert all of the threonine into isoleucine, wouldn't they? I mean, think about it. They would just sit there and convert threonine all day into isoleucine. And then what's the problem with that? Think about it. What's the problem with that? Because the cell wants isoleucine, right? It uses isoleucine to make proteins. But what's the problem with converting all of your threonine to isoleucine? That's right, Wicket. You still need threonine. You can't afford to convert all of your threonine to isoleucine because that's just as bad as having no isoleucine. Does that make sense? So in this case, this is a perfect candidate for feedback inhibition. Does that make sense? This is the perfect setup for a feedback inhibition mechanism. So what happens? The end product, which is isoleucine, not only will the cell use isoleucine to make proteins, but isoleucine it can also serve as the very inhibitor. It is the inhibitor to enzyme 1. It can feed back. That's where the feedback comes in. This product feeds back, binds to the enzyme 1, shutting off enzyme 1. Isn't that neat? The very product of this metabolic pathway can feed back and shut off this pathway. Why would you want to do that? Well, if you've made a sufficient threshold concentration of isoleucine, well, then you wouldn't need to continue making more isoleucine because you don't want to run out of your initial substrate threonine. So you need to feed back and put the brakes on the system. At that point, if you ever do run low on isoleucine, if this product does ever drop below that threshold concentration, then you can free up, that would free up these enzymes to make more isoleucine. Isn't that neat? So you make too much product, it puts the brakes on itself. If you have too little product, it releases the brakes. It's a feedback inhibition. It makes sure that you always have the correct threshold concentration of a product and never too much and never too little. Isn't that neat? So again, the very product of a metabolic pathway is the inhibitor for that pathway. And the only reason you would need that is if you wanted to conserve your initial substrate. Let me ask you this. Let me ask you guys this to put your thinking hats on before the end of the video. Let me ask you this. If the cell didn't care about this initial substrate, let's say this initial substrate was something the cell can't use at all, but it can use the end product. Do you think that pathway would feed back and inhibit itself? Do you think that pathway would have feedback inhibition? No, it usually won't, right? Because you don't care to conserve this initial product, isn't that, or initial substrate? Isn't that neat? So that's feedback inhibition. Again, feedback inhibition, the end product of a metabolic pathway shuts down the pathway. And why is that good? It prevents the cell from wasting resources. Isn't that neat? So with that, I believe we are at the end of our Chapter 8. Thank you for joining me with this new computer setup. I'm hoping I can improve the resolution over the next videos. Thank you for joining me. Leave me any comments in the comment box below, and I'll catch you guys next time.
Dr. D, Dr. D, Dr. D. 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 Dr. D, Dr. D, Dr. D.